if asked. So now the next sessions of this lecture include the spectral analysis of surface wave. Oops. In short, it is known as SASW method. And thereafter, we are going to learn about MASW technique, which is multi-channel analysis of surface wave.
So, spectral analysis of surface wave method is also used to find out the shear wave velocities of the top superficial layers, and it was first introduced in 1980s by the people at University at Austin, and this is also a relatively low cost and non-destructive seismic method for finding the shear wave velocity profiles. And in this method, we do try to use the dispersive characteristics of the Rayleigh wave, and when that Rayleigh wave is traveling through the layered medium. So, this Rayleigh wave velocity, as you know, it depends upon the shear wave velocity, and also it depends upon compressional wave velocity and the material density. So, using the Rayleigh wave velocity dispersion curves, you can model these in order to find out the compressional shear wave velocity and also the density profile of the area up to a depth of approximately 1 to 2 wavelengths. And I have also told you that the longer wavelength can penetrate deeper, and the shorter wavelength can give you the characteristic of the soils that are present near to the surface. So, dispersion in surface wave velocity arises from changing stiffness properties of soil and rock layers with depth. So, high frequency surface waves, that means you are talking about the shorter wavelength. They basically stresses the soil near to the surface and may be giving the value of the shear wave velocities of the shallow subsurface. Similarly, that things are true for the longer period waves that may stress the material at the greater depth and may sample the properties of the deeper material. So, this is the typical field setup of the SASW technique, and this figure is taken from the paper published by Stokwe et al. In 2017. So, you can see there are 3 layers, layer 1, layer 2 and layer 3, and when the Rayleigh wave is passing by, then the particle motion are happening, and based on the wavelength it carry, the sensitivity of the Rayleigh wave may go up to the deeper depth or the shallower depth. For the shallower depth, the smaller wavelength may be used, and for the deeper depth, the larger wavelength can be used. So, basically, if you have the combination of both, that is basically the characteristic property of the dispersion curve. So, you know, like when we are plotting our dispersion curve with respect to wavelength lambda, and you have some phase velocities, so it may look something like this. So, the shallower part or the part that is associated with the shorter wavelength can give you the velocity of shear wave for the layers that are present near to the surface. And if you go to the deeper part, for that purpose you need longer wavelength. And this is the typical field setup that is for the SASW technique, and this field setup is also known as common middle receiver geometry that we used in SASW. So, you can see like there is a source here, and there are some receivers represented by R1, R2 and R3. And in this technique, you are having a source that is vertically oriented, maybe an impact source, random source, or maybe stepped sinusoidal vibration you can generate. So, using this source, the distance between first receiver here and the source is equal to the distance between receiver between the R1 and R2, right. So first you excite the source and you are going to take your reading on R1, R2 and R3. Thereafter you will increase the distance between source and receiver and then keep this instrument onto the other side and then again record your reading. Okay, likewise this pattern will keep on going on. So first you have the distance between the receivers as x, thereafter as 2x, thereafter you have 3x, likewise it will keep on going. So as you increase the distance, it will penetrate deeper and you will have a complete profile of the subsurface. So this is what it says, that the SASW testing process involves using active sources. So in this particular technique you are going to use active sources. Okay, so this particular technique used for shallow subsurface investigations. So active sources to generate surface waves at one location on the exposed material while simultaneously measuring vertical motions on the surface created by the passage of surface waves between pair of receiver. So this geometry, as we just saw, it is known as common middle receiver geometry. The middle receiver is located at the center line of the array and it is not moving during the testing, and if we consider like the area is wide enough where you can move your instrument in a larger space, then you can certainly keep the distance between the receivers double and then triple, then quadrupled like this. Okay, so the distance between the source and the receiver is kept equal to the distance between the receiver R1 and R2. So you can see in the first configuration we were having some distance between source and receiver, and that is equal to the receiver between R1 and R2. Okay, so thereafter after taking the recordings, you have moved this R1 instrument to here, and thereafter you are taking another recording. So now R1 and R2 in the first pair as shown in the previous figure. So at the same time the middle receiver is used as the first receiver in the second receiver pair. So in this case the distance 2x between the source and receiver, first receiver in the second pair equals to the distance 2x between the two receivers in the second receiver pair. So this is we are going to follow. So this geometry of array of the receiver is also known as SASW array, and thereafter the variation in the phase shift, because the vibrator or whatever source you are going to use, that will basically provide the shift in the frequencies, and that will be recorded for the surface waves propagating between the receiver pairs. And for the phase velocity calculation at each frequency, because you are going to compute the phase velocity dispersion curve with respect to frequency, you may use this particular relationship between frequency and the phase angle and the distance between the receiver, and that will give you the phase velocity at a particular frequency. Okay, so as soon as you will keep on moving your receivers away from the source, increasing distance between the receiver pairs, then you will get to have the phase velocities with respect to the frequencies, and frequency you are getting to know from your source. Now after you prepare the individual dispersion curves for this field setup for a particular pair receiver geometry, and thereafter keep on increasing the distance between the receivers, the different dispersion curves are going to appear, and then you are going to superimpose them together in order to find out the dispersion curves for the larger frequency range. And that larger frequency range dispersion curve will be known as the composite dispersion curve, and that composite dispersion curve, that you can use it for modeling purposes. Okay, so when you are computing your dispersion curve for the particular model of shear wave velocity, you may use the inverse theory, and then this is the typical setup that was presented in this paper. You can see there are two receivers, receiver 1 and then receiver 2, and there is another receiver. Receiver 2 is not moving, and there is this sledgehammer source. The person is basically dropping the hammer onto a steel plate, thereafter recording the data. Likewise, you can use bulldozer as well for generating the high energy source for moderate profiling up to maybe less than 75 meter, and also you can use a source where the bulldozer is moving back and forth in order to generate the source energy. And also there is a setup for liquidator that can be used to generate the low frequencies for going up to a depth of maybe greater than 300 meters. So this is what you can use as a source, and the frequency source frequency range of the different sources are written over here. And now what is the procedure? So in SASW testing basically consists of measuring the surface wave dispersion curve. So that is the important thing. So like in SASW, in MASW, in both the techniques, you are going to develop some kind of dispersion curve either in terms of phase velocity or group velocity for love wave or the Rayleigh wave. Thereafter you need to model that dispersion curve. So if you are using a dynamic source, then you can generate your dispersion curve, or you can compute your phase velocities for different wavelength and then plot them together to find out the dispersion curve. Okay, and in this particular technique you can use a software that is known as WinSASW, and this software is useful to do all kind of processing starting from generating the dispersion curve to modeling of your data. So this is the model that you see. This is the model of shear wave velocity with respect to depth, and in this model you can see this is the shear wave velocity is varying with depth up to a depth of around 300 meter or feet. Okay, so 300 feet they have basically developed the model for this particular valley, Garner Valley, and for this developing the model they are following some kind of inversion scheme. So in this inversion scheme, as the person was asking me in the previous class, let's suppose you have some dispersion curve. Let's suppose this is your dispersion curve with respect to period. You have some velocity on the y-axis, and you want to model it. Okay, so what you are going to do? Let's suppose you have some initial idea about the model at the place. Okay, or even if you do not have any idea, you can just take any kind of reference model, or maybe a model that is present at a nearby site, or maybe the model is looking maybe let's suppose something like this. Okay, this is the model that you have taken as a starting model, and thereafter you will give it some kind of search space. Let's suppose you are saying like within maybe 20 or 30% of this model, my actual model may be lying, because the velocities may not be varying that much, because it is from a nearby site, or maybe from the previous some other kind of surveys, you know the velocities, and then you are trying to better estimate the velocities using this updated technique of SASW. So if you have initial model, you can possibly make some kind of model space around it like this. And now this model space, so this space is known as model space. That means you are going to draw a model from this model space. After drawing a model, using that model, you are going to compute a synthetic dispersion curve, synthetic, okay, and thereafter you will compare it with the realistic or the observed dispersion curve that you have recorded using SASW technique, okay, and thereafter after the comparison you will find out the misfit between them. Okay, whatever misfit you will find out, there are several techniques using which you can find out the misfit between these two curves. Possibly you can use the L2 norm of the misfit, or maybe L1 norm of the misfit. If there is outliers in the data, that is, then maybe the L1 scheme may be more useful than the L2 scheme. So the error, once you calculate the error between the observed and the synthetic data, Then thereafter you again draw a model from this search space. Okay, so for drawing the model between the search space, that is a very important thing. For that purpose several techniques have been developed. That is basically comes into the category of optimization. Okay, in the optimization basically you are using local optimization techniques, global optimization technique. So for example, let's suppose you have a error surface and which may look something maybe like this. Okay, this is your error in the data and the synthetic data. Okay, so in this particular error surface, you will see there are some local minimums like this, and you have also a global minimum. So this is your global minimum, and our aim is to reach to this global minimum. Okay, because that is the best model that will basically fit your data well or may represent the geology of that particular area, right? So in order to reach to this model or this error, or the you can say the minimum, global minimum of your error function, then you may use maybe the global optimization techniques if you do not have any idea of the starting model. So global optimization techniques such as maybe you can use very fast simulated annealing, or maybe genetic algorithm, or maybe some other techniques such as the Gray-Wolf optimization. Many optimization techniques are available. Otherwise, if you have good idea about the starting model, then you can use some local optimization techniques such as the gradient descent technique or others. Like, so what is the problem here? If suppose you have your starting model near to the local minimum. Okay, let's suppose your starting model lies over here. Once you apply your technique, then your solution will basically meander around this local solution. Okay, and you will never reach to this global minima. And if you have a good idea about the starting model that may be near to this global minima, then you may basically reach to this global minimum. But in most of the cases, generally speaking, you do not have a good idea, then we generally try to go for the global optimization techniques. Okay, now there is an uncertainty part of it. Like when you are computing your model, let's suppose you have computed your model and you have come up with shear wave velocity. It may also be possible that the shear wave velocity model that you have come up with, there might be other model that may also explain your data well. Okay, so those are also equally acceptable models apart from the best fitting model that you have just searched for it, right? So this is similar to like you can consider like let's suppose if I will ask you ask certain person that okay there is a friend and who is living in Delhi. Okay, I asked someone go and meet my friend in Delhi. Okay, so my friend might be living in a certain house in Delhi, but I did not give him the enough information so that he can find that person in Delhi, right? So the information that I am going to give may work like as data. Okay, so I have given just one information that my friend is living in Delhi. So what will happen? The person will go into Delhi and then try to find out my friend. So there are number of possibilities are there, infinite number of houses are there that he may look out for, right? Then thereafter I will give one more information, okay, he is living in South Delhi. So your solution will certainly reduce to like maybe from 1000 to 500. Okay, so the models are reducing. As soon as you are giving more and more data, your solutions are decreasing. Okay, likewise I will tell them, okay, in the South Delhi on a certain road he is living at. So you are basically what you are doing, you are going to reduce the amount of uncertainty. Okay, so similarly, if you have the dispersion curve and you are fitting your dispersion curve using some model, using optimization technique, then you have found out a velocity model. But other velocity models are also there, like the houses, like the addresses in Delhi, that may also well explain your data. Those acceptable models comes into the part of uncertainties into the model. Okay, there is uncertainties associated with your solution. So you need to quantify those uncertainties using some statistical techniques. Maybe you can use some kind of marginal, posterior probability density functions, covariance matrices, or maybe you can find out the variance, confidence interval, all those things you can find out. Now, what are the key benefits of SASW technique? So, SASW technique has the significant advantage in contrast to borehole, because in the borehole you need to dig out a well bore, and thereafter you are taking the samples out in order to find out the shear wave velocities in the lab. So, in contrast to borehole measurement, which are point estimates, SASW testing is a global measurement. Okay, that is a much larger volume of the surface is sampled. The resulting profile is representative of the subsurface properties averaged over distances of up to several hundred feet. Resolution in the near surface is typically greater because you are doing an active survey here. So, the frequencies will be naturally more. That is why it will be more sensitive towards the shallower depth. So, the resolution for the near surface features will be greater in comparison to the other methods. At sites that are favorable for the surface wave propagation, the SASW method allows appreciable cost and time saving. Okay. Now, if you look at the another technique, so in the previous technique you were using just the 2 receivers, right? Now, there is this technique which is known as multi-channel analysis of the surface wave. Here in this technique also you are going to use the properties of the Rayleigh wave. That means the dispersive characteristic of the Rayleigh wave. So, the field setup basically looks something like this. So, this is the field setup. Okay. So, what you see in the first figure, there is some source, possibly the hammer, and a plate is there, and you are hammering the plate to generate some energy, and the energy will propagate in the form of spherical half wavefronts, and as soon as it will reaches to this array of stations. So, basically you have a source, you have array of geophones here, and also you have a geode. Okay. So, what will happen, like you are recording your energy on the array of the geophone, and the energy being recorded at this array of the geophone will be stored in the digital format into the geode, and you can display the data into your laptop, okay, using some software. Okay. So, after you record the data, all the Rayleigh wave that is going to the receivers can be processed and to find out the final dispersion curve. Okay. This is the dispersion curve that you can find. You can see there is the wavelength, you have the velocity, and after you find the dispersion curve, then you can model this dispersion curve in order to find out the 2D shear wave velocity variation profile underneath this particular array. Okay. So, this is the field setup. So, this how this basically goes on. So, like you are going to find out the shear modulus in terms of the shear wave velocity, which is basically linked to the material stiffness, and it is one of the most useful parameter in the engineering. So, seismically shear wave velocity, the same thing it is written, it is a best indicator of the material stiffness, and you can also use other kind of surveys such as the refraction survey, downhole survey, crosshole survey, but here we are talking about the MASW technique. Okay. The MASW technique basically can be done using the active survey and also can be done using the passive surveys. Okay. So, in the active surveys you are exciting a source by yourself, like sledgehammer you can use it, and you can generate the energy and which will be recorded at the receiver. In the passive survey, you can use the noises getting generated by the traffic or maybe thunder or the tidal motion, and those activities will be passively recorded onto your receivers. Okay, then thereafter you can process your data and in order to find out the dispersion curve. Okay, so when you are using the active MASW, the penetration depth, that means the investigation depth will be few meters, maybe less than 30 meters. Okay, because you are going to deal with very high frequency components. Okay, so high frequencies, that you know that the earth behaves like a low pass filter. That means the low frequencies will penetrate deeper, but the smaller frequencies will remain limited to the surface. That means the shallower depth investigations can be done using the active source methods. So the best solution in order to find out the complete profile of the MASW or the field of investigation, you need to use both the methods together. Okay, active as well as passive. Okay, using active method, you will be able to find out the features up to a certain shallower depth. Thereafter, you can use the passive method that may penetrate the deeper depth, and you will get the profile much deeper also. Okay, now, so this basically again represent the thing that we just discussed. So like in the case you are using so this is the typical field setup in the first figure you can see. So there is this source here and you have array of geophones here, and if you are using active survey, then you are exciting this source. If suppose you are not using active survey, only the passive survey, then the noises generated by this aeroplane or maybe the car, maybe the human activities such as running of the children or maybe some other passive noises may be recorded onto the geophones. Okay, and then using these array of geophone, the data recorded, you will generate this multi-channel records. That means you are keeping all the geophone records side by side, and thereafter you are going to compute the dispersion curve. This is the dispersion curve. So in the color-coded format, using some kind of software such as WinMASW or the surf size software you can use. So using that software, you can basically generate the dispersion curve in the color-coded format like this. Okay, and then after you are converting this dispersion curve into the shear wave velocity profile. So similarly, you can say like the principle is same as that of the SASW method. There also you are basically generating the dispersion curve, and here also you are generating dispersion curve, and finally you are getting the shear wave velocity profile. Okay, now after you get the shear wave velocity profile, you can interpolate. So this shear wave velocity profile is being generated for a particular array of the geometry of the receiver. So for example, let's suppose this is the surface and here you have array of geophone. If suppose it is a 12 channel geode, then you will place maximum 12 receivers along the surface, and you will maybe excite a source here. Okay, and then the receivers will record all the energy. Thereafter what you will do, you will go into the roll along mode. Roll along mode means you are placing this geophone at the back side, okay, and then again exciting the source and recording the energy. So what will happen, at one point you have samples this much section of the subsurface, and another time when you place this geophone into the other side, then you are recording the section up to this much. Thereafter you will again do it like this, and then again keep on going like this. So this particular thing is known as roll along mode. So that is how you are going to cover the entire surface area in order to find out the 2D section. So in the first instance, when you did not move the geophone, you will get 1D shear wave velocity profile from your dispersion curve. Thereafter you move the geophone once at a time. Thereafter you will get another dispersion curve using which you can get another 1D shear wave velocity profile. Likewise, you will keep on doing it up to the extent whatever area you want to cover. Okay, so you have several shear wave velocity profile like this. Okay, and then you can interpolate them together. So when you will interpolate them together, you will see your velocity section something like this. So you can see different colors here are representing the different velocities of the shear wave. So the range of the velocities are represented by this particular color bar here. Okay, so that is how you can find out your shear wave velocity underneath the area of investigation. Now if we talk about the active MASW method, so it was introduced in geophysics for the first time in 1999, and that can produce a 2D VS profile, and it is a conventional mode of survey where they were using some active seismic source. As I said, maybe hammer you can use it, and then you can place your receiver along the linear profile and record the energy. okay, in the roll along mode. And thereafter, surface waves, whatever will be generated by the active source, will be propagating horizontally along the surface of the measurement and from the impact to the receivers, and then you can generate your shear wave velocity profile from the dispersion curve that you are going to compute. So this is a very cost effective technique, and also it is a time efficient technique. And in our department also we do have this setup of instrument, and we do go every year take our student for a winter geophysical field training. There they also conduct this kind of survey and then compute the dispersion curve, and thereafter they also do the VS30 profile. Okay, so the maximum depth of investigation in case of active MASW survey is in between 10 to 30 meter. Okay, and we want to find out at least 30 meter depth of the shear wave velocity. Okay, now for that purpose, because active method was so popular, so there was the demand to basically go to the deeper depth using the same technique, because you are readily getting a 2D VS profile section, and in order to go to the deeper structure of the subsurface area, you need to have some kind of technique or some kind of source that can go deeper. Okay, so for that purpose, this particular technique came into picture, passive MASW technique, where you were using the passive sources in order to find out the deeper investigations. So basically, as the surface wave method is gaining popularity among the engineer and the geophysicists, demand for increased investigation depth is also growing. However, the amount of active source energy needed to gain a few more hertz at the lower frequency end of the dispersion curve, and thereby to increase the investigation depth by several. So basically, so in the, let's suppose this is your active survey. This is your active survey. So in the active survey, you have the high frequency content, right? So high frequency content means a smaller wavelength. Okay, so if suppose you have your wavelength, so this is your frequencies. Okay, this is your velocity. Okay, so higher frequency, so you are basically having this part of the dispersion curve that is basically related to the shallower depth. But if suppose if you want to go to a deeper depth, then you also need to have the other end to be investigated. That means you need to have the value for the velocities of the Rayleigh wave phase velocity for the smaller frequencies. Okay, so for that purpose, the passive MASW technique was devised, and the passive surface waves were generated from the natural sources or the traffic at the low frequencies, and maybe for the wavelength ranging from few meters to maybe certain number of kilometers. And this type of application was basically originated half a century ago, and it was usually used to be named as MSM, that means the microtremor survey method. So this is the particular setup for passive remote MASW. So there are two kind of setup that we can go through. One is passive remote MASW, another is passive roadside MASW. So passive remote MASW, you want to have your receiver geometry in a symmetrical fashion. Asymmetrical receiver geometry is not preferred. So because you will be recording your surface waves or the Rayleigh wave in a particular direction in case of asymmetric geometry of the receivers. So either you can go for the circular arrays, or maybe go for a triangular arrays, or maybe the square arrays, or maybe some other kind of symmetrical receiver array setup. Or if you are doing the passive MASW, so that is the beauty of this method, that you can even do it in a area where there is lot of some kind of crowd is there. Along the roadside also you can do it in a roll along mode to basically cover the entire road in order to image it up to a certain meters. So the passive method, as I told you, employs a 2D receiver array. passive remote method such as the cross or the circular layout to record passive surface waves. This result in the most accurate evaluation of the 1D shear wave velocity at an expense of more intensive field investigation and the burden of securing a wide open space of the array. This can be a good choice if relatively regional 1D VS profiling is needed. So any 2D receiver profile that is symmetric in shape can be used. For example, elliptical or the elongated rectangular shape, you should not use it. Okay. Or if, as I said, you can use circular, cross, or maybe you can use square, triangular, or maybe any other kind of geometry. Now, passive roadside, if we talk about, is a MASW method that adopts the conventional linear receiver array and tries mainly to utilize those surface waves generated from the local traffic, because passive it is. So along the roadside, the traffic will be passing by. So from the traffic, you can record the noise. It tries to overcome the limitations with the passive remote method, such as difficulty in securing a spacious area. Because in case of remote method, passive remote method, because you are going to deal with a specific 2D geometry of the receiver, right? So in that particular case, you need to have a larger space. But in this particular passive roadside method, only a linear geometry of the receiver is being used and relatively less amount of space you are going to use it. With this method, the array can be set up along a sidewalk or the shoulder of the road, and the survey can continue in a roll along mode for the purpose of 2D VS profiling. So using, you can also use some kind of land streamer in order to drag your line along the road. Okay, and this can result in a combined, so I told you, like, so just look at this particular figure here. What you see in this particular figure, there is this passive recording dispersion curve and there is this active recording dispersion curve. Using passive recording dispersion curves, you are getting your dispersion up to certain lower frequencies. Okay, up to this much, maybe you can say maybe around 10 hertz. So this is the one. So this may be, these lower frequencies may be sensitive to the greater depth, but it will not give you the gross idea about the shallower features of the subsurface. But if you will combine it with the active method such as this one, so in the active method you are going to deal with the higher frequencies. Okay, so using the higher frequencies you will be having the dispersion curve for the higher frequencies. So here you are getting the lower frequency dispersion curve, here you are getting the higher frequency dispersion curve. If we model them together, possibly we can have a complete profile of the subsurface in terms of the shear wave velocity with respect to depth, right? So when you will combine them together, that is why this plus sign is there, then you have the entire dispersion curve for a range of frequencies starting from the lower value of the frequencies to the higher value of the frequencies. So once you combine them together and then you can model it, and then finally whatever you will be getting, that will be your the final image. Okay, now what are the some factors that may influence the accuracy of the SASW and the MASW technique? Okay, so the first thing is the testing. Okay, so testing may influence the accuracy. So first you need to test your geophones, like whether they are working or not. Sometimes the one of the geophone is not working, then it may also affect your readings. Now what is the variability of the surface, lateral variability of the subsurface, that also may affect or the influence the SASW and the MASW technique. Okay, shear wave velocity gradient and the contrast. Okay, so it also depend upon like what is the distance between the pair of the geophones. So that will basically affect the resolution of your depth profile of the shear wave velocity. Okay, and the values of the Poisson's ratio assumed in the inversion of the dispersion curve. So as I told you, like you are going to search for a model in the model space. Okay, So that model can be a shear wave velocity model. Also, you can find out the P wave velocity model. Okay, so P and S waves are basically related to each other. Okay, if you keep both the parameters free, then it may also happen that sometimes the P wave velocity goes smaller than the shear wave velocity, and that is not possible. So that is why you will have to link them together with a certain ratio, and that ratio is known, that ratio with which we are going to link it together is basically a Poisson's ratio. Okay, so what we generally do, we are going to have the shear wave velocity as the free parameter and also the Poisson's ratio as the free parameter. Okay, after you find the best model of the shear wave velocity and the Poisson's ratio, using both of them together, you can find out the P wave velocity. So you cannot keep the shear wave velocity and the P wave velocities both as a free parameter. Okay, so that is what they are saying. Values of the Poisson's ratio assumed in the inversion of the dispersion curve is also a factor that may affect or influence the SASW and the MASW accuracy. Okay, the background information on the site geology improves the model. So when we were discussing about the inversion, so while discussing about the local optimization technique and the global optimization technique, so the local optimization technique is preferred when you have a good idea about the starting model. Okay, if you do not have good idea about the starting model and still you are going to do the local optimization, then your result will be poor. Okay, it will be having certain inaccuracy in your results. That is why you are going to have, if you have a good information about the geology of the area, then the local optimization technique can be preferred, and where that which will be accurate also, and also it will be little less time consuming. And if you do not have the idea, then go for the global optimization technique, and that global optimization technique using which you can find out your final model. But still the global optimization technique, if you are applying and if you have a good knowledge about the starting model or the geology, that will also improve the model up to a certain extent. Okay, so these are the factors that may affect the accuracy of SASW. So today what we have learnt in site characterization, when we started, we learnt that you can do your site characterization using the techniques, surface wave techniques such as the MASW, SASW. You can also use the ambient noise survey such as the HVSR technique. Okay, so in HVSR you are going to fit the HVSR curve, okay, using which you can find out how the depth variation of the shear wave velocities is happening. Likewise, you can use SASW and MASW technique, using which you can compute your dispersion curve for the subsurface, and then you can model them to find out the shear. So final aim is to find out the shear wave velocity, either using HVSR curve or the MASW technique or the SASW. You will also find there are many papers, those who basically talks about using the HVSR technique and also MASW techniques together. That means you are going to use the HVSR curve and also the dispersion curves together. So when we were talking about finding the address in Delhi, so we were giving more and more information in order to constrain our search area into the Delhi region. So when you giving the HVSR curve only, maybe whatever model you will get, it will be having a larger uncertainty. That means your model, number of models will be more. As soon as you will give one more information, that means the dispersion curve. So what will happen? The number of models will significantly reduce and your accuracy in the results will improve. Okay, that means you are going to reduce the uncertainty, or your number of acceptable models are going to reduce. So that is what we were doing. So now after doing SASW, where you were using a pair of receiver to find out your dispersion curve, that will give you only a 1D model in SASW. Okay, but if you will keep on doing it for the multiple location along the array, then possibly you can find out a 2D profile in SASW technique as well. But that will be more time consuming than the MASW technique. Okay, in MASW, you are going to find out the dispersion curve using maybe 12 channel of geophones, 24, 48 or 96 based on the availability. And then if you do conduct the active and the passive MASW techniques together, then it will give you the lower end of the frequency range for the dispersion curve, and also for the higher range of frequency range for the dispersion curve, and then you can model them together in order to find out the shear wave velocities. Okay, so this is all for today. You have any question, then please go ahead.
Of B, right? So that is what we call it as a joint probability, right? So this is the formula for the joint probability. Now let's see, this is a set. This set has a 1, 2, and 3. Say A1, A2, and A3 are the three emit in that set, just like your stove as a TVS, and that's it. They don't have a fourth TV, so that means that stove has only 3 TV, and that is the all. Okay, so that means this sample space only has 3 outcomes, right? It cannot have more than 3 outcomes, right? So that's why it is called sample space is called the exhaustive event. So that is A1, A2, A3 are the mutually exclusive, but it is called also exhaustive because they exhaust the entire sample space, right? And then there is another event which is called the under repair, and that under repairment is this is your B. So B is the repair probability. Sorry, B is the repair probability, right? So these things is the A1 and B. So right, so this is your A1 intersection of B, right? Because this is the common part of with the A and the B, right? And then this one is the common part for the A2, right? So this is equals to probability of A2 to the B, right? And then this is equals to some comment. This is equals to the probability of A3 and B, right? So the probability of B, if you can calculate, then that will be equals to probability of A1 intersection B plus probability of A2 intersection B plus A3 intersection B. Intersection B. So that you all add up, then that is your probability of B, the whole probability of T space, right? Still. Makes sense? So this is what this part. Now let's see if I if I say like this way that something what you should just okay, now let's see if I need to find out that if I say that okay, I have purchased, but this is your B condition A. So that means I have purchased the ATV, the condition I purchased the ATV. What is the probability of it is come for the repair, right? So purchase the ATV or A things, and what is the probability of its repair, right? So that means that will be equals to the probability of A intersection B divided by probability of A, right? So that's the things. So that means that is your prior probability, right? So basically this is your joint probability, this is the prior probability. Now you think in a different way. That means I am trying to say that I have coming for a repair. Then I need to calculate what is the possibility that it is coming for ATV, right? So then that will be equals to the probability of A intersection of B divided by the probability of B. Now, this probability of B means it is basically the sum total of nesting. But it is this, but it have in they do that with that. And you literally should do that because sometimes you see that the lab works are more giving a much better signal in line with trouble than but then the other moves than the thing sensing. So you will get what SH and SB sites. But actually Manish is doing dissertation where he is using surface ware. So you're not using active source or passive source. So yeah, some passive source. Passive source energy you are using two but seven. So what is the aim of your dissertation? So like I want to assess the structure transfer. You took the previous last. What will the effect on the structure while we are like, in the case of blasting is the after workers or that blastings. So like there is some buildings that are affected due to blast system. So what is my aim to correlate with the PGV in vector velocity from the meter the blasting and correlated with the nature heat itself and correlate with the like how it will impact like it will be resonant some kind of application, some time mitigation. That application will devastating the structure. So I will just reduce those devastating parameters. That's the thing. I will last year I discussed with the sir for predict. I want to develop prediction model, not prediction model. PBB and the peak ground extent, PSCAT PPH. So there is a part of similar project for the like there is a destructive transformers. So like I can add there is a one chapter in our dissertation. So can you give some insight on this? Like after you were talking about you want to develop those ground motion model. Yeah, ground motion model. For the ground motion model development, you need to have some strong motion data. Okay, acceleration data. You have it. So I have a PPV dash. I don't have acceleration dash. Models. So basically, you need to which will collect those data, or maybe you need to request some agency that might have collected the strong motion data in your area already. Yes. Okay, there are sites like PESMOS, POSMOS. There you can look out for the data. There the data might be available for some stations or something. So what is your area of research? I mean region. Regions are outlasting sites at some magic areas. Helping. Anyone else is doing similar kind of work or maybe site characterization? Okay. So in the second half, starting from 3 p.m., we are going to use the Geopsy software to develop HVSR curve using some data that we already have. And thereafter, we will do the modeling to generate the shear wave velocity profiles. So we have already shared the link with you all on the WhatsApp group. Kindly download and install the software before you plan. Anything else? Okay, thank you so much. That is all. And sorry.